Hello everyone. Continuing our series, which was on random forest, we were on episode 12. This series is on machine learning fundamentals. We were on to random forest classifier, and we had explained random forest to a great extent, and in fact, the related concepts that are there with random forest classifier, those we had taken. Some of them purely conjectural concepts. We had taken the background and theory and rest of the comparisons which are there. And with that, I had in fact showcased and demonstrated one simple example with random forest classifier, that was the student's performance. So we shall be going forward from the same point we left. Some of the important aspects, few more important aspects that are there as far as random forest classifier is concerned, and certain aspects which are yet to be, in fact, discussed. Those will be discussed initially in this particular episode 12B, and then we will finish it by giving one advanced example on the random forest classifier, which is related to medical diagnosis. So one example which we had given earlier, that was related to student performance. So let me just display this screen to you. I am having certain slides first of all. So I think 4 to 5 slides first of all before we can go to that program, and I'll be explaining in fact in detail that program, and then we can just see what random forest is providing us. So this is going to in fact underpin exactly what we require. We have discussed random forest in quite a detail, different aspects of this, some of the important things which are there. So these are important parameters which we are going to discuss now for random forest. Um so one is these estimators, which we discussed to some extent last time, and then we have used them in the program as well, where we are using 10 estimators. These are the will be using how many decision trees. This will decide when we are putting the estimators, number of estimators. This is actually designating that how many number of decision trees this random forest is going to use. So this is a very important aspect of random forest. More number of trees normally will be giving you better stability. But you have to, there's a in fact trade between the stability and the performance. So if you are having more number of trees, it might be equally impacting your performance. So that is something which we will be discussing at the final slide. That you have to just see. But more number of trees normally will be giving you, as far as the parameters and matrix of matrix performance matrix of a particular machine learning algorithm, or for that matter random forest is concerned. It will be better if we are taking more number of trees. That means estimators will be more. It will give better stability. So that is number one, very important parameter. I think whosoever is using this random forest, this is one aspect, one parameter which they always need to remember, very important, and this will be having a direct impact on the matrix performance of the random forest. Then we are having max depth. The limits. This limits how each tree can, how deep each tree can grow. This is not something which is specific to random forest only. It is for the decision tree, similar kind of a thing. We have seen the depth there as well. So it helps reducing the overfitting that we know. We have just seen that in how in fact decision trees are taking care of that. But here as well, more number of as more deep you're going, that is again going to have impact on the performance. And random state 42 is something which where we want to get this I can just say constant result outputs, otherwise. So this is by convention we are putting it 42, as we have explained in the earlier episodes as well. So this is making output repeatable. Otherwise, you will be getting, you will not get any stability. You'll see that there's a change, a rapid change in each time you are running. So for that, we are using this state, and you are aware about this. And then there is OOB score. which is equivalent to true. This is one more very important aspect which you need to learn, and this is, in fact, specific for a random forest, as far as now we have introduced it. So random forest trains each tree using a random sample. So that we learned in the last episode itself, that random forest is using, each time it is training a tree, it is using a sample of data which is different. But there are certain records out of the data which are left, which are not included in any of the trees which are there. So these left out records are used for internal validation. So this is giving you one more chance, or you can just say a random forest is getting one more, one more such that such testing kind of a thing, where we can just see the validation of the model, how better it is performing. So this OOB score gives an OOB score is giving an extra estimate for model performance without needing a separate validation set. So without having a separate validation set, this out of the bag score, this is called as out of bag score. So this out of bag score is giving extra estimation way for the model's performance, and we don't need a separate validation report for that, validation set for that. So because it is creating that out of bag score on the data which has not been used by any of the decision trees. I think a very important aspect which in fact everybody should be remembering. And then going forward, what is the comparison of random forest if you just see with others? So other ensemble methods, if you just see. So random forest versus bagging. Random forest adds feature randomness at each split, reducing tree correlation. So this is one advantage which random forest, in fact, in the first previous episode as well, which is 12A. In that one also we had discussed it, that this is adding some correlation. So random forest versus boosting. So ADA boosting, XG boost is there. Random forest trains trees in parallel independently. So this is one thing which one needs to just remember, and how understand the difference between the XG boost and the random forest, while boosting trains sequentially with error correction. So there is a difference. It is treating each random forest trains trees in parallel. So but boosting trains sequentially with the error corrections. So this is one difference which is there. And when we are talking about gradient boosting and random forest, if we have to give a comparison of these two, a random forest is more robust to overfitting, so it will be handling overfitting in a better manner. Gradient boosting often achieves higher accuracy but requires careful tuning. Sorry. So this is careful tuning is required for gradient boosting. Normally, it happens that when we are having comparison, that is also going to happen. In fact, maybe not to such an extent, but when we are taking, for example, some other series, there is a series, for example, in medical diagnosis, which will be taking, for example, different algorithms that can be used, and then comparing their results in different data sets. There, it will be, for example, for the sake of comparison, when we are, taking multiple algorithms, there we will come to know that, for example, gradient boosting is there. It achieves higher accuracy rates. Then it might need some level of tuning. That is definitely there. But as far as random forest is concerned, it is very robust, especially to overfitting and all. You can just say it handles overfitting in a better manner. Performance optimizations, we know this, how to enhance the performance, because one aspect of machine learning is which is a very important aspect. In fact, it's not just about taking something and running a program and getting those scales which are there, metrics, performance metrics, and getting them up. It is having impact on the resources, and in a particular use case where you are having continuously these things running, it can have significant impact on the resources, and that needs to be taken care of, certainly. And it is not a test bed where we are just testing something. It will be it will be in fact having an impact, and then it has huge resource implications, which will be having a direct impact on the investment of a particular organization, how much they are investing on a particular project. So when it comes to these real world realistic scenarios, so definitely at that time you have to just think about optimization, and your solution should be optimized. So first thing which is there in the optimization is parallel processing. We can just use parallel processing for this. Utilize all CPU cores for parallel training, so that can be done so that we can optimize our execution happens faster, and then we are able to complete a particular task in an optimum time period. Feature reduction. So what we can do is the features which are there. For example, the data set which I'm going to show you now, which is related to breast cancer. And we are our random forest classifier, and in fact there's a comparison to decision tree as well. So that random forest classifier is classifying whether a particular feature, a particular patient with which is having these, it's having almost 30 features in the data set. We are using the default one which is there in embedded. I'll be just telling you how to import that as well. So that is that particular the features which are there. So we should be able to choose those features, so minimum level of features. So reducing the max features which are there, that will again have impact, because if you're having too many features and then you're faster training with minimal accuracy loss, so we need to just see if we are reducing those features so that our optimization, performance optimization can happen. But at the same time, we should not be losing any accuracy. So this is one more aspect, very important. And then depth control. In fact, we have discussed it to some extent earlier as well. That limit maximum depth to prevent overfitting and speed up training. So this is overfitting should be definitely that will be we can control it. We don't need to go unnecessarily too much of depth. We don't need to go for. So that will that is, but it should not be too less as well. That will be resulting in we have just seen that case. In fact, in underfitting. Optimal level of depth, which will be good for performance as well as for handling the overfitting. And sample controls, definitely use minimum samples for split, minimum samples, samples leaf, and warm start for incremental training. So as far as the samples are concerned, if you're having huge samples and all, that is again going to have impact on the performance, and then we should be having some sort of a control on that as well. So this is one more very important aspect. Three, four aspects, important aspects, which are very important to remember, that is there. And now, what are the key takeaways? So we are almost concluding this random forest. I'll be showing you a detailed example. I'll just explain first of all what it is, and then I'll be producing the results, interpreting them in front of you with confusion matrix and other parameters which are there. In fact, random forest is providing us certain things which are very critical and very important to understand the performance. So, what is the motivation for random forest? Ensemble learning, overcome single tree instability and overfitting, which is there, which we can see in decision trees. So, that is some motivation, a huge motivation, which will definitely, encourage us to use random forest classifier for variety of different applications. And I will just showcase you maybe the applications. Earlier I had shown it. What are the application areas for the random forest? Implementation and evaluation, hyperparameter tuning, and bias variance trade-offs can be done in this particular area. Core concepts are there: bagging, feature randomness, and majority voting mechanism, which we have discussed, in fact, in detail. And then advanced topics, OOB, which we discussed, and what OOB is. OOB error, tree diversity, and best practices. So these are actually the takeaways which are there. And in fact, I'll be just showcasing you now the I'll showcase you now the program which is there. One random forest program we had taken earlier. This is one more. That was a very simple example which was related to students' performance. We were taking the data also which was used there, that was not having many features. It was having, two, three features, four features, not more than that. But this data set which we are using here, we are using the breast cancer data set which we are getting from sklearn. So it is showing here from sklearn data sets import breast load breast underscore cancer. So this breast cancer data set which is there, which is have it's a it's having quite a large data set which is available there. It is having number of features also, almost 30 features are there in this one. We can just see that. You can just make it view as well if you want. So you can just display the data, maybe certain rows of the data. You can just make it display as well. You will be exactly able to get the data. At least that you can just see the nomenclature of this characteristics of the data which are there. And then rest of the things which are there, we are bringing both decision tree classifier as well as random forest classifier, importing both of them because we are using both of them in this particular program. And then the rest of the things like classification, confusion matrix, and accuracy scores, that is something normal which we have done in the previous programs as well. So what I'm saying is that you load this data set. So data is equal to load underscore breast underscore cancer data set. So it is loading that, and then I am putting the value of x, initializing, and then data shape, and I am just printing this first few rows, maybe 5 rows. I am just printing for the data, so you will just see that as well. And then I am just saying that x dot head I'm printing first 5 rows, so that is fine. And then the training happens. So split data into training and testing. I'm doing that. So this is training and testing. I'm splitting. I'm taking 25% for the testing and 75 for training. And random state I am mentioning 42. That is something which you already know. Then we are training the single decision tree first of all. So single decision tree, if you just see, this is a decision tree classifier. This is not for the first time we are doing it. And we are training this, and here we are taking the depth as 4. That means it will be taking levels which are there. This decision tree, it will be having 4 depth. That is normally we have taken before as well. So this is the training that happens for a single decision tree. This is what how we are doing it, explaining this, and then model fit, and then prediction. So this is what is there. And then we are have training the random forest classifier here. So random forest classifier, we have now this is for the second time we are doing it. We are using estimators as 200, not done before. We have used in the previous example 10 estimators. Depth we are using 6 here, so that is in fact a little more. Random state 42, so that is the same thing. And OOB score we are putting it on true. That means it will be just giving us one more estimation in fact before the test. And then class weight balanced. So we are putting the class weight as balanced, and then we are training this model again here. So that is the random forest classifier. And then we can compare the accuracy. So what is the accuracy of the decision tree and the random forest classifier? See, I'll tell you one thing at this point in time. When we are saying the accuracy of even 0.2% in certain cases is very huge. You leave aside 1%, 1.5%, or 2%. That is very high. Because in certain critical cases, even if we are having 0.2% of accuracy, we are talking about, for example, 1 million patients. There's going to be a huge number of patients will be getting impacted by that. So these are critical areas in which for example certain predictions are happening. So that is going to, even if it is in decimals, for example 0.1%, 0.2%, not to talk about 1%. If it's a 1%, 1.5% difference, that means it's a huge advantage over the other. So that we have to keep in mind. So dt underscore accuracy score, so it is giving that these two parameters, and then it is putting this the print decision tree accuracy is this one, and this random forest accuracy is rf underscore accuracy. We are first of all evaluating this accuracy into two variables, and those variables we are printing them simply. Then it is showing that how much percent accuracy is. That's what we are trying to display here. And then random forest out of bag score also will be given. So that is also given by rf underscore model dot oob underscore score. and then underscore again. So this is calculated by the system itself. You can just see all of these are included here. You can just see them. So whether we are talking about accuracy or something else, all of them will be included, in fact, and they are defined. And Then we are having confusion matrix. So confusion matrix is not for the first time we are doing it. We are printing this confusion matrix as well, and classification report as well. We are printing. We are giving that target names. Okay, so this classification report also is there, and then we are having the prediction which is there. So sample patient prediction, patient class, and then we are probability of malignancy and probability of being a benign. Benign is a normal thing, so malignancy is abnormal. This will be showing us that probability of a particular case. First of all, we are predicting whether this is going to be a benign or this is going to be malignant, and then it shows that if it has reached to a conclusion. For example, it is showing that a particular case of breast, this is benign. So what is the reason for that, and what is the probability of that being benign, and what is the probability of that being malignant? So that is something which is there, and then the feature importance which is there. Which feature was important? This is something which is very unique with random forest. It's not just giving you one parameter or certain parameters which are there, for example precision and others. It will be telling you out of the features which are there for a data set, which feature has played a significant role, and how much what importance and significance that feature is having. So that also will be there. It will be displayed, and we are trying to display that with this particular graph. So if we can just see, this is there. So we are putting it figure, and then that figure will be displayed, and I'll be showcasing you the figure. So this is a comprehensive program where a data set which is having almost 30 features that will be taken into consideration. This is a data set of this breast cancer data set, which is available inbuilt, and then definitely we are going to utilize that with the random forest, and we'll just understand it in a better manner. Let me just first of all run this, and I'm running this. So we'll just see what results, and then we can just have an interpretation of that. First of all, it is putting this first 30 row, 5 rows, for the data. You can just see it's having huge number of features as well. So 5 rows and into 30 columns. So you are having 30 columns. So that means 30 features are there actually for this. So decision tree accuracy is 94.4, and random forest accuracy is 95.8. That means 1.4, which is a huge thing, I think. In my opinion, that's a huge 1.4 is a huge difference, huge improvement. Random forest out of bag score is 95.77%. So out of bag score which is there, that means tested on the one data which was out of bag, which was not taken as a training data for any of the random forest trees. On that one, when it was performed, it gave the accuracy of 95.77. That is little, I think it's almost same what we are getting accuracy now. So that means those results are correct as well. You can just see those, compare. And this is the confusion matrix. I have interpreted it multiple times. 49 of those cases which were benign, and they have been declared as benign by the model, and then 4 of them which were benign, but they were they were predicted as malignant, for example. So this is what is there, and then we have done the interpretation before as well. Malignant precision 0.96, benign 0.96, recall is 9298, F1 score 9497, and support 5390. So this you can just see all of these sample predictions. The sample which was predicted now, which we had given in fact, is the class which is benign, and probability of malignancy in this one was 1.77%, which is very less compared to probability of being a benign benign this disease. So 98.3, so it's a non-cancerous. Benign means non-cancerous. So 98.23%, which is significantly much higher than what was here. So it is a simple case that it's a benign. Then there are top 10 important features which we have to see. So these are the top 10 important features which are contributing some 15%, 13%, 10%, 10%, 7% like this. You can just see that. I'll be showcasing you this graph which we have put on this. So if you just see the worst parameter, these are the features. Oh, definitely for the data set, these are the features. Now, to understand these, how important they are for a particular breast cancer disease. So for that, you should be having, in fact, a specialist in that who will be telling you that this worst area, concave points and the rest of the things which are there. So mean concavity, how they contribute to a particular disease, in fact. But you can just see model itself is telling you that these are the features which have contributed. So if you just see almost one model is having because 30 features are total there, but top 10 contributors to this we can just see, I think ranging from 4% to 16% different. So these are having a significance of 4% here, and the 16%, almost 16% here in this one worst perimeter. So this is giving you actually one more very important aspect which random forests is having, which we are not having anywhere else, that it gives for each of the features how much significance, because then you might be able to, in certain ways, as we are saying, uh, uh, enhancing the performance by eliminating those features which are having very minimal significance as far as the results are concerned, because you can get that. So minimal significance, those it is giving you top 10 for example features which are there, so they contribute maximum to what is there, and we can just identify those which are not having much of a significance, and those can be eliminated to enhance the performance. That's I think this is the this is we have concluded this second part of random forest classifier, and I think it's very clear, certain concepts which we have taken, some of the related concepts in random forest, why we are using random forest, what's the reason for that, how it is giving, how it provides benefit over decision trees, and the difference to some other ensemble methods as well, and then implementation in Python using a very simple example one, and then one advanced example, and then giving a comparison of what kind of results and interpretation can be done on those when it comes to a random forest classifier. So please keep watching this particular channel, to subscribe to this. It will be giving you an alert whenever a video gets uploaded to this channel if you're subscribing. And then we will be just moving forward with this the machine learning, and we are having some other series as well coming up in this, which are specifically there for fraud detection, anomaly detection, cybersecurity, for computer forensics, and then there is a series which is there for medical diagnosis separately, so that we'll be able to discuss all of these things in much higher level, at much higher level, comparing different data sets and different machine learning algorithms and their performances. That is something we'll be just going, so those series will also be available here. So keep watching this and subscribe to the channel, give us your feedback so that we can improve. Thank you so much once again for joining. See you on the other side.